Well, hello everybody. Guess what? It's the last official lecture of your Calculus 2 career. Welcome. This is it. Okay, what we're going to do is we're going to talk about polar functions. All right, so remember polar functions like, let's say, r of theta equal, I don't know, 4. Remember that one? Probably not, but that's okay. Remember that just describes a circle. So you hand me a theta, and I'll give you a radius. And this is just a circle of radius 4. Okay, something like this. Now, if you want something a little more compelling, you'd have something like, say, I don't know, r of theta equals, let's go 2 plus 2 cosine of theta. Remember how that worked? That's this guy. So you plug in, I made you guys, you hated me for it, but I made you put in these little coordinate trees. Remember you had a theta, and you had an r, and you start at 0, and the cosine of 0 is 1, so it's out here at 4. And then at pi halves, we know cosine of 0 is 0, so we're up here at 2. And this thing goes like this, kind of. It goes, and then this thing was called a cardioid or a cardioid. I always screw it up, so I don't try to do it. Now, notice, this is a whole different way of trying to describe a curve. Remember when you first learned it back in pre-calculus, you're like, what the heck is this? Now, can you imagine? Now, think about this. How would you integrate this? How would I find the quote-unquote area under the curve? Well, A, it's not a function, so talking about area under a curve doesn't even really make sense. It's very tricky to break this down as a function. It's not like, you know, one of those like a parametric or something like that. It just doesn't work that way. Excuse me. So what we do is, if I want to figure out the area of one of these guys, if I want to figure out the area, quote-unquote, let's say bounded by the curve 2 plus 2 cos theta, it's actually really simple, and it has everything to do with a circle. All right, I'm going to presume that you don't remember. Oh, that's just terrible. You know, sometimes I draw a really wicked good circle, and sometimes not so much. I don't know what you remember from your pre-calculus days, but I'm going to presume not too much. Do you remember there was something called a sector? And a sector, oh, that's awful. And a sector was just a pizza slice. It was all this in here. And let's say that we've got an interior angle, or a central angle. I guess interior is not quite accurate, is it? A central angle of theta and a radius of r. If I want the area of that sector, all it was 1/2 r squared theta. That's straight out of your pre-calculus book. All right? Now, we're going to use that idea. All right? If you think about it, if I want to figure out the area really between this curve and the origin, all right, do you agree that what I could do is I could start there and I could trim that out, and that thing would look approximately circular. This curved part of the curve, excuse me, that's ridiculous, this curved part of this function, remember it's a polar function, it's still a function. You plug one theta in, you only get one radius out, you can't get more than one. It looks very much like one of these guys, only it's really thin, right? Well, what would the area be? Well, if it were a circle, it would be 1/2 r squared theta. Now, think about how we built areas using integrals. Think about how we built areas using integrals. Well, I'm going to do exactly the same thing here. The question is what is this guy? It's certainly not a fixed theta, because it's going to be here, and then it's going to be here. And if you think about it, what am I eventually going to do? I'm going to thin this guy down, this really long, skinny pizza slice. I'm going to put an uncountably infinite number of infinitely thin, you're starting to hear me, aren't you? Pizza slices, right? Like that. All right, oops, they should come out here, not like that. Like that. We add up an infinite number of infinitely thin things. God, that just smells like an integral, doesn't it? Now, again, the question is what is the angle? Well, the angle is, well, what do you think it is? It's going to be delta theta, right? So instead of having, let me change this. Change the color over here. Instead of having area equals 1/2 r squared theta like we would for finding the area of a sector on a circle, what we would have is this would be the integral of 1/2 r squared, so whatever r is, that's this guy right here, whatever r is, it would be 1/2 r squared d theta. Oh, by the way, I kind of misdrew this curve a little bit, because we know at pi, we know that cosine of pi is -1, so this thing should actually come curving in a little bit like that. It's going to do this. It's not going to be pretty any way we do it, but it is what it is. I draw them horribly. And that's true. The coolest thing about this, ladies and gentlemen, is that is true for any polar equation. Now, it gets a little trickier, and we'll play with that in class more as we move. But it gets a little trickier when you get curves that overlap. And we'll have a couple problems like this. Now, remember, the point of all this is to find the area bounded by this curve or these curves as we explore more and more curves. So the question is what are my limits? Well, my limits are just like any other limits. It's going to be from A to B. And just like before, just like when we first started this whole debacle, the question is where is the action taking place? Well, for me to make one full lap around this whole curve, right? Where did I start? I started when theta was 0, right? And I got 4. So that starts me right here, doesn't it? Then at pi halves, it was 2, right? At pi halves, it was 2 because cosine of pi halves is 0, 2 plus, yeah, you got it, right? And then it goes to 0 at pi, and then it wraps back around. Think about that. All right, what happens at 3 pi halves? At 3 pi halves, it's 0 again, so I wrap all the way around 3 pi halves, and then I get the cosine is 0 again. 2 plus 0 is 2. So I'm down here, and then at 2 pi, I come all the way back around. So this cardioid does its full business from 0 to 2 pi. Now, if I don't understand the behavior of the curve and that it completes itself, so to speak, its cycle from 0 to 2 pi, my area is going to be off. Okay, let's take a look at this thing real quick, and then what we'll do is right now we're going to find the area, and then excuse me, and then we're going to play around a little bit on the TI and see what we can do. All right, so let's find the area that is bounded by a cardioid, or I guess another way to say that is what is the area of the interior of a cardioid? Well, according to the rules, I'm simply going to go the integral from 0 to 2 pi of r squared. So this is going to be 2 plus 2 cosine of theta. Now, let's be careful. I'm getting crazy over here. D theta. It's 2 cosine squared, right? And then d theta, because delta theta becomes d theta. And then, of course, don't forget your 1/2 out in front. Now, I'm going to flip over to another page so I can work a little easier. The area is the integral from 0 to 2 pi. Stick my 1/2 out in front. I'm going to get 2 plus 2 cosine of theta squared. Remember, this is r squared. And then d theta, this comes from delta theta, right? Delta thetas, as soon as I start counting up an infinite number of infinitely thin things, they become d's rather than deltas. It's just like what we've always done. All right, there's nothing new here. So let's see what happens. I got 1/2, the integral, 0, 2 pi of 4 plus what, 8 cosine of theta plus 4 cos squared theta d theta. Cancel my 2's. This becomes a 2. This becomes a 4. This becomes a 2. So this is the integral from 0 to 2 pi of 2 plus 4 cosine of theta plus 2 cos squared theta d theta. Right? Now, I'm going to do this parenthetically because I don't know how many of you have gotten fantastic at this, but watch. Remember cosine squared. I'm going to keep that 2 because it's going to be really useful. Cosine squared, another way of writing it is 1 plus cosine of 2 theta over 2. So this guy boils down to this guy, and look at that, my 2's cancel. Isn't that awesome? So in a quick little puff of algebra, notice I'm going to have a 1 plus cos 2 theta, and I'm going to have a 2 over here, so this becomes the integral from 0 to 2 pi of 3 plus 4 cos theta plus cos of 2 theta d theta. And I can finally get to work. Look at all this algebra I had to do before I could do a dang thing. So this becomes 3 theta, right, not 3x. What, minus 4 sine of theta, right? By what? Oh, I guess that's, what am I doing? It's Sunday night, you guys. This is my last, I came in on Super Bowl Sunday to do my last lecture, right? So you're going to have to bear with me a little bit. 4 sine theta, and then plus sine of 2 theta over 2, and this is from 0 to 2 pi. Now watch what happens. This is awesome, because what I end up with is 3 times 2 pi, right? Plus, now sine of 2 pi is 0. Sine of 4 pi is 0, so I'm going to get plus 0 plus 0. Now here's the fun part. Minus 3 times 0 is 0. Sine of 0 is 0. Sine of 0 is 0. And guess what? The answer is 6 pi. Isn't that awesome? Now let's see if we can make our calculator work for us a little bit. All right, so what we got to do? 2. Oh, I did 5. What the heck's going on here? I got to fix that a little bit. Let's go. I'm going to scooch over here, put a 2 in there, and then I'm going to graph it. And there she is. Now, it's kind of hard to see. It's kind of a pain in the butt. If I wanted to, I could zoom in right there, and we could see how it kind of pops in right there. You'll see how it drops in like that. Now, I'm going to zoom back out. I'll do well, actually, you know what? Well, let's do it. Sorry, I'm getting a little crazy with myself today. Let's go zoom standard. And then I'll square that up. If I square it up when it zoomed in, it'll square up the zoom in. So zoom square. Let's see. Yeah, a little bit better. Still a little bit hard to see. Sorry, you guys. I want to make this as pretty for you guys as I can. I know I'm driving you nuts, but that's my job. And that's close enough. Now let's see if we can do some calculus on this thing. All right. Yeah, see, that's kind of a bummer, huh? Because all I get is I can't take integrals with this. But we already did the heavy lifting on the integral. We already know that the area right here, if I go back to the graph, the area bounded by this curve is 6 pi. Piece of cake. Ladies and gentlemen, that's it. I gave you a nice short one for your last one. Hey, thanks, man. It's been a pleasure. I hope you've enjoyed the lectures. Again, yell at me if you want to see something different for next year, if you think other students would enjoy a different approach to stuff. This is my first year through, so if you want to see something different, something more, something less, just let me know. All right. Have a good day, and thanks for your time and attention. I'll see you tomorrow.